Hello everyone, welcome to Physics Rocks. It's true. Tonight it is energy types and efficiency. So let's get started. Okay, so basically we talk about energy all the time. We talk about energy when we're getting light from the sun. This is the sun. Okay, we talk about energy when we get heat from a fire. We talk about energy when we eat a sandwich. This is going to take a little bit longer on the drawing of a sandwich. Trust me, the graphics get worse from here on in. We talk about energy when we're talking about going for a run. This is the worst stickman ever drawn. Okay, do some speed lines. There we go, running. When we're talking about energy, we're talking about lots and lots of different things. There are different types. They all have the same thing in common, and that is that they can cause a force and cause that thing to move. But what are the different types of energy when we're chatting about them? The list, as you need for your GCSE, is pretty short, but we still need to know what they're all about. Okay, so the first one is chemical energy. Okay, this is the energy that we talk about when we're talking about food, when we're talking about solid and liquid fuels. And this is the energy that we get from chemical reactions. Okay, so if we're talking about chemical energy, this is what we're talking about. Broadly speaking, it's not much use to it. Use to us. It tends to be stored inside stuff, and then we release it as other forms. Other forms of energy are heat. Right, that's the stuff that you get from fires, from radiators. Okay, you go out on a sunny day. What's that lovely feeling you get? That's heat. Okay, then we get electrical energy. If you plug it in, it's electrical. If you get zapped by it, it's electrical. Sound energy, what you're hearing right now. This is the energy from noise. Okay, this is the movement of particles that hits your eardrums and your brain then interprets it. Light energy, that's the energy that triggers the retina on the back of our eyes to send messages to our brain, and we interpret it as pictures. Okay, this is light energy. Magnetic energy. If you hold a magnet next to another magnet, they push apart or they pull together. There's some form of energy there. That is a type of energy. Then we have strain energy. Right, this is not the type of energy when you're trying to have, a number 2 and you're working really hard at it. This is the energy that we have if we squash a spring, or we pull an elastic band, or we bend an object but it really wants to jump back into position. This is strain. Kinetic energy. Right, from the Greek for movement, this is movement energy, where we get our word cinema from. If we're moving, we have kinetic energy. And then finally, gravitational. If I could spell gravitational, that would help. Gravitational potential energy. Those are our energy types. Gravitational potential energy, if I lift something up from a low height onto a higher height. So let's draw ourselves a little shelf. Right? If I take a little object and I put some energy into it, I give it some movement energy, and I set it up there. Right? I've spent some energy getting it up there. If I push it off, it starts moving again. Where did it get the energy to move from? It got its energy from gravity. We put energy in, it got stored by gravity. This is called gravitational potential energy. And then when I push it off, gravity takes effect and then converts that gravitational potential energy back into another type. Now, I've already mentioned a few times about converting energy from one type to another type. And this is pretty much what this whole lesson is about. It's about the idea that we can take something that has energy in basically any of these forms and turn it into energy of another form. I can take heat energy and turn that into kinetic energy. I can take electrical energy and turn it into sound energy. I can take magnetic energy and turn it into gravitational potential energy. But there are some rules and there are some problems associated with doing that. And the biggest problem associated with doing that is something called the principle of conservation of energy. Okay, the principle of conservation of energy. Right. And this states that energy cannot be created or destroyed but can be changed from one form into another. Okay, that's pretty important. Okay, energy can't be created or destroyed, but it can be changed from one form into another. The total amount of energy in the universe right now is exactly the same as it was the instant the universe came into being. We'll talk about that at another time, but the universe came into being. Right now, we're staying laser focused on this idea. All right, so let's change energy from one form into another. Okay, so let's take something dead simple. Okay, something you've run about with all your life. Let's take something like an electrical heater. Okay, so electrical heater. All right, nice and simple. Right, now what our electrical heater does is it's going to take energy and it's going to draw in some energy and it's going to output some energy on the other side. Right, the energy that an electrical heater is going to take in is electricity. Okay, so let's say something like an electrical fan heater or something like that. Okay, what it's going to output is it's going to output heat energy. That makes sense. All right, let's assume it's a fan heater. Okay, it's also probably going to output some movement energy. Okay, it's going to spin a fan blade around. That's going to be useful. And that's wonderful. Everything is exactly how we would like it to be. The unfortunate downside is that basically anytime you take one energy type and convert it into another energy type, you're going to lose some energy in the process. And I don't mean destroy it. I mean, you're not going to be able to convert, let's say, 100 joules of energy of electricity on one side into 100 joules of heat, or at the very least 100 joules of heat that's going to go out into your room and heat it up. You're going to get some wasted energy, right? So at the very best, you're going to get like 50 joules of heat, say, and maybe 30 joules of movement. And those of you who are really quick off the mark on the maths will go, wait a minute, 100 went in, only 80 came out. What happened to the other 20? Because you said you can't destroy energy, and you are very clever and correct. What actually happens is that we get some waste energy dropped out the bottom of this system, and that is sound energy. Okay, or it could be any other type, but in this case, sound energy we're going to go with as our primary wasted energy. That's 20 joules, say, of sound energy. This is simplified, but it's pretty good. All right, so we got 100 joules going in on this arrow, 50, 80, 100 joules coming out. So our principle of conservation of energy is spot on. Now notice what we've done here. We've established that sound is wasted because an electrical heater is probably not designed for your enjoyment of the noise that it makes. That's not what it's for. It's for making heat and movement energy, sort of. That's to distribute the heat around the whole room. Okay, that little fan motion thing to get it going faster. But usefulness and not usefulness are human defined terms. If you turn on the electrical heater because you really like the sound of the fan, then sound isn't wasted. Right? But what we can't say is that we get 100% conversion from one type of energy to another. We normally say that anything that's not the way we want it to be is wasted. But what we want is very much up to us. So when we say waste, that could change. Classic example is like a light bulb. Light bulbs take electrical energy, they convert it into light and heat. We say that the heat is wasted. Not necessarily. You might like warming your hands over the top of a light bulb. Who knows? But what is true is that the electricity didn't get converted from one form into another. Now, electricity is the wrong terminology here because we should be using our correct styles of energy. So we get electricity. That's not in our list at the start, but electrical is. So let's update that so that we're talking about energy here. So this is electrical in here. Heat and sound are in the list, but movement is not. Movement is just a little bit too vague. We want to call this our technical word, which is kinetic. This is an energy transfer diagram. Energy transfer diagrams are surprisingly useful at telling us just exactly how much energy we're putting into something and how much we're getting out. This setup is quite nice because it has any wasted energy dropping out the bottom and our useful energy continuing from left to right. Okay, just the way we read, so that's kind of intuitive towards us. If you're being super graphical about it and you like being a little bit artsy, what you can do is you can put your object here, and then you can use arrows of various sizes that will actually give you the right thing. So let's say we put in quite a large amount of energy. Let's go like this. But then when we get our outputs, maybe we have arrows that look a little more like this. And by drawing block arrows that represent the correct sizes, and even if we got them down to the point where we're talking about areas inside here, we can make pretty detailed diagrams that are rapidly visually appealing. In this case, we're saying we're producing a little bit more waste than we are actually producing useful output energy. Okay, you can see that at a glance. We don't even need numbers on this. Happy? I hope so. So this whole idea leads us to talking about, well, how much energy do I get out? How much energy do I put in? And that's the comparison that we really want to make. There's no point telling you, like, here's a machine. So let's draw ourselves a little machine. Okay, boom, boom, some little bits of that, some little buttons on it. There we go. We've got a lovely machine here. Right? And this machine outputs, this looks like a sound-based machine, so let's say it outputs 500 joules of sound over a given time. Is that good? I don't know. Is this worthwhile? Is this a good machine? I have absolutely no idea. But if I draw the arrow going in, let's say this is some form of like crank up system. So we're going to put some kinetic energy into it. I have no idea how we would do that, but let's say you have to turn these dials and sound comes out. Right, so we're going to spin this round that makes sound. If I have to put in 550 joules of energy, well, I'm losing 50 joules of energy. I don't know if that's good or bad, but we could agree with that. But what we could say is if I had to put in 10,000 joules of energy to get the 500 joules out, that would be worse than having to put in 550 joules of energy. And why is that? Because 550 joules is, what, 10% bigger than 500? Whereas 10,000 is, what, 20 times bigger? Right, so this one's better. If we could get it to 550 for 500, that's a better return on our investment than 10,000 getting 500 out. Now looking at these numbers, we can do that kind of in our head normally, but what we really want to do is have numbers associated with that. And this is where the concept of efficiency comes in. And efficiency is defined as it is equal to the useful energy you get out divided by the total energy that you input. And this is given as a fraction. Okay, useful output energy divided by total input energy gives you your efficiency. Now, the word energy can be substituted in lots and lots and lots of different places. This word energy can sometimes be substituted for the word power. Okay, because power is energy per second, as we will find out later on. Okay, so power, energy, you can put those words in there. To be honest, you can put in money. Okay, my useful output money divided by my total input money, that will give me the degree of efficiency for my money. You know, you could have even simple words like revision. My useful output revision divided by my total input revision. Now you know about that already, where you're sitting staring at a book and none of it's going in and it's been a complete waste of your time, whereas when you're really focused for like 15 minutes, but that entire time you've been learning, that's actually more efficient. So we're using the word energy tonight, but the concept of efficiency can replace this word with anything really. Alright, so what we end up with is, let's take our example there. Let's do efficiency, and we're going to shorten that to EFF, is equal to my useful output energy. But we're going to assume that the sound was useful. So let's say that that was 500. And we're going to divide that by our total input energy, which was 550. There we go. Alright, time to grab our calculators on this one. Got my snazzy Physics Rocks calculator in my hand. I'm going to do 500 divided by 550, and that is going to give me an answer of 0.005 0.90, and that's going to be recurring. So that's 909090. So we'll round that off to 0.91. Okay, so we did that calculation, put that over there. So my efficiency equals 0.91. Right, 0.91 doesn't look like a good number, but this is a decimal number. Let's convert that to a percentage. All we have to do to convert something to a percentage is multiply it by 100%. So that's times 100%. And that gives me an efficiency equal to 91%. 91% in anybody's book's good. It's an A star in your GCSE exam. We'll take that. Now let's do the other situation. Let's try that our efficiency is equal to, once again, we had an output of 500 joules of useful energy. Notice that we had an actual output of 550. Okay, 50 of it was wasted as something, but we're not interested in that. We're only interested in the useful output energy. So 550, this time it was divided by 10,000 if I remember right. Let's check back just to make sure. Yep, 10,000 there. So 500 divided by 10,000. And this time my efficiency, once again grabbing our calculator, we hit 500 divided by 10,000, and that's going to give us 0.05. Right. Multiply that by 100% to quote it as a percentage, and that gives me an efficiency equal to 5%. That's certainly a long way down in 91%. If you get 5% in your GCSE exam, that is bad news. So this is how efficiency works. Okay, so what we want to do here is we want to try and use this, so let's try and do an example. So let's try an example. E.g., let's say a toaster takes in 800 joules of electrical energy and outputs 450 joules of useful heat. What is the efficiency? Okay, cool. So what I need to do is I need to identify what's going on here. I've got a couple of energies. So I've got takes in 800 joules, so we're going to highlight that. And I'm going to put outputs 450 of useful heat. That's good news. Okay, we've already been given our useful. So let's do a little abbreviation. Efficiency equals. Now writing useful energy out or useful output energy is a little bit annoying, so we're going to put useful output energy, so UOE, divided by total input energy. Okay, so all the vowels go on the top line and then your tie goes in the bottom. Okay, so useful output energy divided by total input energy. The total bit's important. Put the numbers in, we get efficiency equals useful output energy is 800 divided by, sorry, try that again, the useful output energy. So the efficiency is equal to the useful output energy, outputs 450, divided by the total input energy, which if I remember correctly was 800. Just check my question, there it is. So my efficiency equals, once again we grab our calculator, 450 divided by 800 gives us 0.5625 as our efficiency. We don't want that as a decimal, probably. We could quote it as a decimal if we weren't asked for anything else, but we like percentages, so we times that by 100% to give me my efficiency equal to 56.25%. And that's all there is to it. The occasional sneaky examiner will try something like this. That will go for a system is 40% efficient. I was going to go 50, but that's too easy. It's 40% efficient. And outputs 300 joules of useful energy. What was the input? Okay, so again, we know that this is an efficiency question. We've done our revision. We know our equation. Efficiency equals useful output energy divided by total input energy. Do our division sign. And let's work out what we've got here. Efficiency equals 40%. But this equation doesn't deal with percentages, so we're going to make our little list over here. That's equal to 0.4 as a decimal. If you're in doubt, just divide by 100%. Okay, hit divide by 100 in your calculator. My useful output energy is equal to 300. My total input energy is what I'm trying to find out. Let's call it X, because this is an algebra problem. Let's do it. Right, so instead of efficiency, I've now got 0.4. Instead of my useful output energy, I have 300. We still have our division sign. We still got our fraction. And instead of total input energy, we have X. So solving this, well, we don't like this X in the bottom line, so we're going to multiply both sides by X, so times X. We'll make that a capital X. And times X on both sides. That gives me 0.4x is equal to 300. But we don't want 0.4x, we want just x. So what we need to do here is we need to divide both sides by 0.4. Because 0.4 divided by 0.4 gives me 1. So that's 1x, or x, is equal to 300 divided by 0.4. You head back to your calculator and you get 750. So my answer here is 750 joules, and I can just check that's reasonable. A system is 40% efficient, it outputs 300 joules. What was the input? Well, the input's 750, that's bigger than the output. That's a good clue that you're on the right track. Simple as that. Alright, next thing to do then is grab yourself down in the link below the little worksheet for this evening, have a crack at it, and come back to me in a couple of seconds when you've got that done to see if you've got the answers right. Good luck to you. Okay everyone, welcome back. Now we need to complete the energy transfer diagram for a light bulb in a bedroom. Include one waste energy type, so one only. So what we need to do is we need to go, right, we're definitely going to get one input type of energy, we want at least one output energy, and we say we want one waste energy. So our diagram is going to look like this. So what goes into a light bulb? Well, electricity goes into a light bulb, so we're looking for electrical energy. So electrical energy goes out. What comes out of a light bulb? Clues in the name. Light comes out of a light bulb. It's in your bedroom, so it's unlikely that you're going to be using it for heating purposes, so light's the useful form out here. And then we need a waste energy. The light bulbs don't tend to make too much sound, they don't make any chemicals, they don't do any nuclear stuff, so we're left with the waste energy out the bottom as heat. And that's it. That's all we're looking for. Electrical, light, heat. Jobs are good. On to question 2. An electric motor draws 50 joules of electrical energy to lift a mass. The mass gains 15 joules of potential energy and the rest is wasted. What is the efficiency of the motor? Okay, well, if it gains 15 joules of potential energy, that's gravitational potential energy just shortened. That's the purpose of the motor lifting it. Okay, so this here is our useful energy output. This is our total energy input. So away we go. Efficiency equals useful energy output divided by total input energy. Or useful output energy, as we've been saying throughout this, so we'll get it the right way around. So my efficiency equals my useful output energy was 15 divided by my total input, which was 50, giving me an efficiency equal to, hop on the calculator, 15 over 50 gives you 0.3. You could leave it at that, but we like things as percentages, so that gives me an efficiency equal to 0.3 times 100%, which is 30%. And then finally, number 3. A power station is 30% efficient if it outputs 150 megajoules of energy every second. What is the input energy every second? Okay, so here we go. We've got output energy and we've got efficiency. We've got this weird every second thing going on here, which we might want to be a little bit concerned about, but it's input every second and output every second, so the time scale is the same. So we can pretty much ignore that and just deal with it as a 1 by 1 second thing. So once again, we're back to efficiency equals useful output energy divided by total input energy. So this time though, we know our efficiency. Our efficiency is 30%, which is 0.3 as a decimal, is equal to my useful output energy. Now, there's a real temptation here to go 150 megajoules, that's 150 million, especially because this little hint has been given. And that's something of a red herring. We can actually do this in just megajoules. Okay, we'll try and be aware though that our answer at the end will also be in megajoules. You can convert it, it's no problem at all. It's 150 million, you just end up with lots of extra zeros. So we do our output energy is 150 divided by my total input energy, which we don't know, so we're going to call that x. Multiplying both sides by x gives us 0.3x equals 150, and then dividing both sides by 0.3 gives me 150 over 0.3 gives me x equals 500. Okay, the unit here though is megajoules because I didn't convert to start with, so we'll get an mj. For the sake of completeness though, we'll do it as if you did, so that'll give me same first line, useful output energy over total input energy. My efficiency therefore is equal to my useful output energy, which was 150 million. So, and we'll do this as a proper division-y thing. It'll look a bit weird, but we'll do it anyway. Not that line, this line. And we want that again over x. Okay, our efficiency was 0.3, so we can replace that in here as well. And what we want to do is we want to multiply both sides by x again, just as we did before. This will give us, get it lined up nicely, 0.3x is equal to 150 million. So x therefore equals, divide both sides by 0.3, and we end up with 500 million. But in this case, this is just joules, and this is 500 megajoules. Hope you got these ones right. If you liked this video, hit the thumbs up, consider subscribing for future content. If you didn't like it, you know where that button is. Leave me a comment down below. Either way, are we liking this new style of format, or do we prefer the live stuff? I appreciate your time and your effort this evening. All that remains to be said is, don't forget, ladies and gentlemen, physics rocks. It's true.